Hello, ATO. It's nice to be back in Raleigh after a few years. So, I suppose that my marketing manager wouldn't let me get away from the concept that I need to introduce myself, so here it's in brief. I had the distinct privilege of spending basically my entire career in open source, aside for a brief stint in academia. I'm the product management director for CEPH at Red Hat. Previously, I was the Ubuntu server PM at Canonical. And if you roll back into the previous decade, I was also the dreaded systems management czar at SUSE, which is a lizard reference that will only make sense if you ever use SUSE distributions. Here are a few things that I worked on. Obviously, CEPH and Ubuntu I already mentioned. Landscape is a systems management tool for Ubuntu that's actually quite neat. Ximian Red Carpet used to be a systems management tool for early Linux distributions, also very neat. SMT is another systems management tool for SUSE distributions. Obviously, I worked on SUSE Linux Enterprise alongside Ubuntu. Those are my Linux distributions so far. And I've been the maintainer of man for about 10 years. I suppose technically I still am, but we're using Collins distribution in preference these days, so that seems like the thing to do. And I'm joined by Anna McTaggart.
Hey, I'm Anna McTaggart. I use they, them pronouns, and I'm a senior security analyst at Red Hat. I did my undergrad at UMass Amherst, graduate school at UC Santa Cruz. I'm a little bit more early career, but I've done a bit of research in grad school on areas ranging from programming languages to file systems, and for the last 2 years, I've been working on storage security for CEPH at Red Hat. I also had the formal methods community of practice where we like to talk about how to formalize things and logically think about code. I am currently working on incident response, and in my free time, I like to hike with my dog, I like to garden, and I like to work towards a more inclusive world.
And we actually have a third speaker, although he never seems to get travel budget to join us. That's Mike Hackett. He is actually the hero of CEPH support, if you're a CEPH customer of Red Hat, so he is no doubt suffering through some customer ticket right now. So we're going to skip his slide, but he is an equal contributor to this work. So if you wandered into a CEPH and ROOK session without knowing what CEPH and ROOK are, this is your 1-minute primer. CEPH is the dominant software-defined storage solution in open source. We like to think of CEPH as the future of storage, as the Linux of storage, depending on what hat we're wearing, and we're very proud of the community that we built around it and its technical prowess. CEPH stands out because it's very highly scalable, it's horizontally scalable, it's also economically scalable. It doesn't cost you an arm and a leg when you cross certain boundaries like other products that I could name. That's why there are more than 3 exabytes of CEPH out there. Some people like to say that there are more than 5, but I'm a little bit more conservative. Many more things can be said about CEPH. It's a fairly complex system and has a lot of things that you can tune and adjust. It's the bee's knees if you are a storage person. But you're here, so hopefully you know that already. And if you don't, we have some resources for you to learn more about that. Less famous, but equally awesome, ROOK helps reduce the operational burden a storage team faces by delivering cloud-native storage for Kubernetes. It's essentially a CEPH operator in a Kubernetes cluster. With ROOK, CEPH is deployed as an overlay atop a storage cluster, atop a compute cluster. So you have a lot of flexibility in terms of your storage and the drivers because they're both installed atop the compute. Maybe this is not the best strategy for sheer performance, but it is a very flexible strategy when you're going to use a limited amount of storage, which is what Kubernetes clusters tend to do today. Also, ROOK enables you to use external CEPH clusters when you graduate to using petabytes of storage. So you can essentially do both things, or transition from one to the other using the same tools. I think that's about it. It's a CNCF project. It has graduated, so quite cool. And the combination of the two gives you what is essentially what products Red Hat has in this space at this point. So let's jump into security practices by component. So security practices harden a specific point of the infrastructure. Cherry-picking practices without a model of the threat and who the attacker is going to be is usually not a viable strategy. You either make the system unusable or you leave some pretty open gaps. The joke usually goes, if you want to protect from all possible threats, you pour your computer into a box of concrete, you drop it at the bottom of the ocean, and you leave it off. In other words, absolute security is not something that's usable. So you do the highest security possible for the threats that you're actually facing. This is usually defined in a threat model. So are you facing script kiddies, or are you facing the GRU, or a privileged insider, which is probably something that we should all be worrying about. Once you have that model of where the threats come from, then you cherry pick from the hardening guide what is that you're going to do to reduce your exposure. Some attackers may want to steal your data. Others may want to cryptolock you and hold you for ransom. Others may just be happy to disrupt your operations. So these are very different threats, and you need to respond to those accordingly. So let's dive into what the hardening practices actually look like. Starting from the network. In a Ceph cluster, the public security zone is an entirely untrusted area of the cloud. It could be the internet as a whole, or just networks external to the control of your IT team, something that you have no authority over. Data transmissions crossing this zone should make use of encryption. Note that the public zone, as I defined it, does not include the storage cluster front end, the Ceph public_network, as it's called, which defines the storage front end and properly belongs in the storage access zone. Now, the Ceph client zone refers to networks accessing Ceph clients, like the Ceph object gateway, the Ceph file system, or block storage. Ceph clients are not always excluded from the public security zone. For instance, it's possible to expose the object gateway. The object gateway's S3 or Swift interface in the public security zone to provide object storage. Next, the storage access zone is instead an internal network providing Ceph clients with access to the storage cluster itself. Finally, the cluster zone refers to the most internal network, providing storage nodes with connectivity for replication, heartbeat, backfill, and recovery tasks. This zone includes the Ceph cluster's backend network, called the cluster_network in Ceph. Operators often run clear text traffic in the cluster zone, relying on the physical separation of the network or on VLAN separation. And here is a good example of modeling the threat. This kind of clear text traffic, even on the separate network, wouldn't be an acceptable choice if you're shielding from privileged insiders. They may be able to tap that network. Well, if you're worried about script kiddies, obviously it's perfectly fine. So again, you need to model what the threat is. These four zones are separately mapped or combined depending on the use case and the threat model in use. So while Ceph can do anything, at least aspirationally, but today can already do a lot of things, object, file, block, different protocols, I don't know, iSCSI, native block, and so on. Most clusters are not doing all things out of one cluster. So you can tighten the perimeter based on the use case that that cluster is serving. A lot of customers separate clusters to limit blast radius. So they could serve object store and block storage out of the same cluster, but they don't. So that if something happens to one cluster, only one of their use cases is affected. That comes in very handy when you're defining your security model. Now, components spanning the boundaries of two security zones with different trusts or authentication requirements must be carefully configured. These are the natural targets for an attacker because they are crossing points between different security levels. So if you can exploit one of the nodes sitting across these boundaries, you could basically privilege escalate from accessing a more restricted network to one that is less restricted. So components that sit at the boundary between network zones should meet the requirements of the highest security level, obviously. In many cases, the security controls of how you access these components should also be a primary concern due to the increased attention on these components from anyone trying to escalate whatever access they manage to get into the network already. So operators should consider exceeding zone requirements at integration points, which for a storage product is often easier to accomplish. For example, in a storage system, only certain operations are happening. It's not as open as a compute cluster, or you can have random workloads running in there. In a storage cluster, very defined operations are happening, and they are following very specific protocols. So there is a lot of room to secure things. For example, the cluster security zone can be isolated from other zones easily because there is no reason for it to connect to the other zones. Conversely, an object gateway in the client security zone will need to access the cluster security zone's monitors on port 6789, all the OSDs on ports from 6800 onwards all the way to 7300, and will likely expose its S3 API to the public security zone, port 80, 443. So there are very different behaviors depending on the component. Don't use one model for all. And I'm going to hand over to Anna now.
Hey everyone. Now we're going to talk a little bit about product security and how Red Hat does this for Ceph and other practices you can use for Ceph. Briefly, product security at Red Hat follows a secure development life cycle with the goal of reducing risk and improving security for both Ceph and ROOK. We suggest improvements, we pen test, we manifest all, and I mean all, of our dependencies. We review vulnerabilities and track weaknesses and exploits. We approve errata releases, checking all the details, review all new releases. We check any new library for CVEs. This was previously one role that was done by several people. Over the past year, we've recently split it into incident response and security architect roles, and we did this in part to ensure really good geographic coverage. So I'm not online at midnight. My colleague in India is, because that is his work day. And similarly, he's not online at midnight. And this prevents any lapses, and it also helps us better cover all stages in our software by making the workload more manageable and people-friendly. So I'm in Product Security's incident response currently. It's one branch of this system. We respond to incidents so we can release fixes in a timely manner. This means a lot of working with engineering. We have to investigate every vulnerability to make sure that a seemingly minor one isn't severe, or vice versa. We aren't telling engineering, here's a red light, you absolutely need to drop everything and fix this, and then it turns out, oh, this doesn't actually affect our code that badly. So we'll work with upstream as well to ensure that flaws are fixed there, contributing to the open source community and helping make upstream stuff better. We try to coordinate all publications to prevent disclosing a flaw before engineering's aware, especially for higher severity ones, so that nobody's surprised by a sudden critical, as much as is possible when we're in charge of it. And in some cases, even waiting to publish till we have a fix ready. We keep an eye out for exploits that are discovered well after a vulnerability is published, sometimes years after the fact, in case it affects what should be fixed or what isn't fixed. And recently, we open sourced our plan for all this, how we respond to incident response. We created a template to open source and share with industry. You can find it in this URL, which will be available when the slides are published. You can probably find it by Googling Red Hat Product Security Incident Response. You'll probably find the blog that I wrote, and you can probably find the link there. It's on MITRE. It covers our process for responding to incidents, and we're sharing this in the hopes that everyone in the industry can benefit from this open source ethos of sharing how we respond to incidents and just generally improving our processes, and we welcome feedback there too. On the other side of things, our security architect works to improve CEPH prior to release by working on the design of CEPH to make it more secure. We manifest all of our dependencies, both with a manually generated list from engineering and automatically with tools that we wrote to ensure that we don't miss even the most obscure container pulling something as part of a build that isn't even used anywhere, but an attacker could theoretically exploit. We manifest everything automatically and manually. We carefully review all major releases and new libraries for CVEs and vulnerabilities in general. We review all exceptions to security policy to approve or deny. We work with our compliance team to validate CEPH to our security policy and assorted standards, such as the federal standards, etc. We've improved our cryptographic algorithms used in CEPH, the improvements to Messenger 2, and work on other design choices like key storage improvements in RGW. We work with upstream, we work internally. Our general goal is to ensure that CEPH is built as securely as possible. That's what product security at Red Hat looks like. So moving on beyond our own product security department, how CEPH does encryption. Server side, operators are overwhelmingly choosing to encrypt our data at rest using the Linux Unified Key Setup Mechanism, better known as LUKS. All data and metadata of a CEPH storage cluster can be secured using a variety of DMCrypt configurations. Almost all of Red Hat's customers choose to do so. We implement security best practices by locating our monitor daemons, our mons, on separate hosts from the storage daemons, OSDs. This ensures anti-affinity of the keys and the data they encrypt. Also, this means that our drive or our host is physically separated from its decryption keys. If you get one, you don't have both. You can't just decrypt the drive if you don't have the key, and you can't just get the key if you don't, like just having the key, you can't just decrypt a drive. The object store gateway has additional capacities, including encryption at ingestion time, the use of per user keys as opposed to per drive keys, key rotation with tools like Vault. We support Amazon AWS, SSE KMS, and more. Even the Department of Defense ciphers certified under FIPS 142 can be used as supplied in RHEL. Now, what about encryption in transit? Well, for encryption in transit, network communication can be secured by turning on CEPH protocol encryption in the Messenger version 2.1 protocol introduces Nautilus, which ProdSect helped improve. And here, clear text can be common and fine, even without the encryption, but encryption is an option. But clear text is common and fine because the networks where the cluster uses the CEPH protocol, you're usually physically or logically isolating them from access. It's not just something that's available over the open internet. And we don't think that that's a huge issue, and there's certain risk benefits and trade-offs there. Compatibility and overheads are the main reasons why back-end protocols are not encrypted. In most use cases, the overhead isn't a big deal, the performance impact is insignificant for a properly designed cluster, but if you're worried about compatibility, it may be a concern. In general, with performance, though, the latency is overshadowed by network communication if the CPU overhead is accounted for properly. So we have encryption, even if it isn't purely necessary due to our security zones, as previously discussed. It's a great option for many people. And if it isn't right for your use case, you're still protected. So now let's look at some more specific protocols here for encryption in transit. For the S3 service, it's usually secured between RGW and the S3 client with TLS on port 443. You can use plain HTTP on port 80, depending on the nature of the data being served. If it's public data, yeah, you can use plain HTTP. But if it's confidential, you can use TLS. One special case that I'd like to make note of, TLS termination at the HA proxy, it's a special case. The link between HA proxy and RGW is in clear text. It has to be located within the appropriate security zone, as Federico was talking about earlier, so that we can properly terminate it. Of course, with the network as well, standard network practices like firewalling individual nodes to only expose a cleared list of ports apply. You still have to keep in mind the security zones, but we have all these awesome security options for data in transit. Now, we're not just going to talk about CEPH today. We're going to talk about ROOK-specific stuff. ROOK can use custom resource definitions, CRDs, to encode many of these settings. You can configure your trust certificates with your RGW's web server. And ROOK also supports at-rest data encryption, just like we discussed earlier. We have the in-flight CEPH protocol in encryption 1.9. Also, our Kubernetes user permission system applies to all persistent volumes. Permissions, quotas, all that good stuff comes from Kubernetes. Nothing Rook needs to do here. Rook also supports key management systems in the container storage interface driver, allowing individual volumes to be encrypted with their own key, limiting the scope per key, which is a really important best practice. All of this above ensures that we can follow best practices easily. We can follow key rotation, key revocation, and limiting the scope from each key. This limits our scope of our unencrypted traffic, and it limits the scope of each key. And then for the control plane here. As popularized by Ansible, SSH is used by ceph-admin, Ceph-Ansible, and other development and day one tools to provide a secure command path for install and upgrade operations as part of host management. We do this so that the dashboard is not usually exposed to the world, but the operator workstation can reach it. Lastly, the manager supports the whole infrastructure and needs to be reachable on the storage access zone, hence why we allow SSH. This sort of covers the details of how exactly we do it, but that's sort of the general high-level idea. Now, what about identity and access? To talk a little bit more about that, going back to Ceph, Ceph's use of shared secret keys protects clusters from man-in-the-middle attacks by default. Good practices are still needed. A good practice here is to grant keyring read and write permissions only for the current user and root, with client admin user restricted to root only. It's generally considered a best practice to not allow all users to be root, and following the above prevents that. Talking now about RGW, it supports the key and secret model of AWS S3 and the equivalent model for OpenStack Swift. Now, of course, the administrator's key and secret should be treated with appropriate respect, and again, use administrative, not just root, users sparingly to reduce your risk profile. You don't want to make every user an admin user either. The RGW user's data is stored in Ceph pools, which should be secured, as we just discussed previously, regarding data at rest. In addition, to further increase security, we can couple with OIDC providers such as Keycloak. We can back them with your organizational identity provider for an even better granular role or attribute access. All of this really ensures that our identity and access models are pretty secure against most forms of attacks and that we're following best practices. Also, we support LDAP and Active Directory users. We highly recommend using secure LDAP if you're going to go that route. We support OpenStack Keystone to authenticate object gateway users. This syncs really well with our OpenStack connections, and just in general, these are some great options that we have for authentication so that only authorized users can access the data that they're authorized to access, and it isn't just all public, and also so that not everybody is root. And in addition to access, auditing is a really important part of security. Operator actions against a cluster are logged. You want to periodically remove these. You also want to periodically aggregate them to your log management system as appropriate. Here, we have some examples of how that might happen. And on that note, I'm going to pass it over to Federico for data retention.
So, one more thing. Let's talk about data retention policies. With Rados, which is the backend of CEPH, end users don't generally have the ability to read, write, delete objects directly in the storage pool. Seems to be out of order. Oh, no, okay, that's fine. And you can apply a bucket object lock, so all objects in the bucket have the same security requirements. You can have MFA requirements to remove objects. It's a little bit different on the CEPH block device, object gateway or file system. Users can create, delete, modify volume images, objects, and files. And when we delete data from a CEPH cluster, it cannot generally be recovered for practical use, but there are exceptions here. RBD has what we call a trash bin facility. So you can delete images and they may sit in the trash bin until that space needs to be reclaimed. So you can configure to have the trash bin or not. That's something that you should be aware of. It's essentially a delete undo facility. It can be useful in some cases. But the important bit about user data retention is twofold. One is on RGW, there is outright versioning of buckets. So you create an object in an RGW bucket, you delete it, you create it again. You have this entire history and all the existing versions in a bucket that's configured by default. If you don't want data retention, you have to configure the bucket not to have this versioned history. Finally, there is the lower level issue, which is in Rados. Rados is another object protocol at a different layer from RGW. And what you have in this case is that you cannot delete objects out of Rados by overwriting them. Because when you write a new object, you're going to create a new allocation. So you also cannot delete them by filling the cluster with writes. That is not going to be good in another way. So how do you sanitize data when you want to decommission media? The most obvious solution is that you use something that is physically destroying the drives, like a degosser or even a shredder. But that often interferes with the ability to RMA drives under warranty. So what is found to be the most effective policy here is that you encrypt the drives. Even if you don't care about encryption, you just encrypt the drives, because then when you decommission the drives, you delete the encryption keys, and it's as good as destroyed. So that is a good sanitizing best practice, even if you don't care about the security provided by encryption, to encrypt your lowest level of the hard drive anyway, because it gives you an easy way to decommission the hardware. Also, when you want to look at it at the lowest possible level, SATA devices have built-in deletion capability. You can issue a SATA instruction to self-delete if you buy drives from the right vendor. So that could be a non-destructive way to sanitize your drives. And the other thing that you can use that's more modern, this capability is like 2 decades old. The more recent one is that solid-state drives have onboard key management. So they can take care of their own encryption, and as long as you manage the keys, you can essentially do exactly what I was saying, but internally to the drive, and say, forget the encryption key for what you currently have, and that will take care of disk wiping, essentially. Hardening options are also a lower level concern, and they are highly vendor dependent. The following are Red Hat's choices. Other Ceph distributions will vary. We ship with SE Linux on by default in enforcing mode, which should absolutely surprise no one, given that SE Linux is a religion around where we work. And we can make use of FIPS 142 ciphers if the operating system is configured to provide these ciphers exclusively. So that's useful for compliance in government environments. Hardening of binaries is also of interest. Red Hat Ceph Storage uses the listed options for hardening binaries. And you can try out kernel-supplied options like seccomp, pi, and all of the ASLR and related options, but these are kernel-derived. So if you use RHEL, you have those. If you use Ubuntu server, you also have those. If you go with some more exotic Linux distributions, it's up to you to figure out what level of operating system hardening do you have. All of these efforts generally make Ceph a pretty robust open source storage solution from comparing with other things out there. And it's certainly the only one that can aspire to serving tens of petabytes out of a single cluster. Generally, there are only two products that are common out there serving tens of petabytes out of one cluster. And I guess I can say that they're both owned by IBM, but this is the only one that's open source. So at scale, Ceph certainly stands out for that. Now, on that note, we're happy to take any questions or clarify anything that we may have rushed through.